Very good. Welcome to this first class on this course on information physics. The idea of the course is going to be mostly about talking about probability and entropy and how to process information and how to use all of these concepts to formulate laws of physics, to tackle the very foundations of physics. One of the things we're going to see is that the range of applicability of these notions in physics is enormous. It essentially covers the whole of physics. So this is the big picture. Let me switch over to my tablet so that we can start writing down. The course is about probability, entropy, information, and how we apply this, all of this, to the very foundations of physics. Indeed, a good chunk of the course is going to be how do we apply all these notions to tackle the foundations of statistical mechanics and of quantum mechanics. So the big picture here is going to be something like what's science all about? Science is a human endeavor to help us navigate the world in a more or less rational and systematic way. The problem is that we have incomplete information. So when we try to figure out how to deal with the world, most of the time we don't know what we're doing. But what is it that we want to do? So what we want is to process reasoning with complete information for the purpose of, well, what do you do when you do science? Prediction. You want to predict how things are gonna happen, whether the planets are gonna move in one way or another, or how atoms are going to react, or various things. You want to be able to predict the future. You also, once you can predict, you can probably see that if you manage to control initial conditions in an experiment or in a process, and you can predict what's going to happen, this allows you to have control over the world. So control of the world. And finally, it's not just that you want to predict what's going to happen and you want to have control over it. You also want to explain what's actually happening. Now, these are pretty weird words. What does it mean to explain something? One of the things that we're going to see as we proceed in this class is that an incredible amount of it has to do with the meaning of words and the philosophical issues that arise behind these words. Well, when we say explain, basically it's going to be something like tell a story. Be able to put words onto what are the processes that are happening out there, and build a story around them so that we don't have to compute with equations all the time. So that's when we say explain, we want to be able to say that a particular process fits harmoniously with other processes, other phenomena that we know of in the world. So here we have an interesting, nifty definition of what science is. Science is reasoning with incomplete information for the purpose of prediction, control, and explanation. There are three problems here that we have to tackle in order to be able to do this in a more or less um, uh, systematic way. But before I even say that, please notice that I'm saying science here. I mentioned physics before, but in all sciences you want to predict, control, and explain. So a lot of, and in all sciences you have incomplete information. So part of what we're doing here is talking about features of science that are completely general. It is true that physicists have managed to be the most systematic about how we handle this. The social sciences perhaps are the less systematic. But nevertheless, this is something that's common to all of science. So what are these three problems that we have to address? The first problem is to represent a state of incomplete information. Mathematically, how you do that? Actually, it's highly non-trivial. When you want to reason about something, you normally do deductions. If I know this, I can deduce that. But if you don't know this, what can you deduce? It seems like a trick question. What can you say when you don't know what to say? In fact, this is historically one of the issues that prevented the theory of probability from being systematically developed from the very early stages of humanity. Definitely, the ancients didn't know anything about probability. They were so unaware of the various uh, nuances of probability that when they had games of chance with the equivalent of what we now call dice, they never managed to decide that it was important in a game of chance to have the faces of a die be equally probable. They would use bones that are completely asymmetric, but it never occurred to them that you should that the odds with which you should use to bet on the outcomes of these random devices ought to be weighed in peculiar ways. Otherwise, you were necessarily going to lose. So there is a historical issue here that's actually very fascinating. How can you reason when you don't know? That's what we're going to be doing. The second problem, oh yes, and what is the solution to this problem? Well, this is probability. Probabilities are introduced as a tool for reasoning under conditions of uncertainty. Now, this is a tricky one. You notice I said tools. So in a very, very real sense, what we're going to be involved in the next couple of weeks or so, I mean, most of the semester in a sense, is in designing these tools. It's a process that's very, very similar to doing engineering. You design a bridge for a certain purpose. You want it to be over a particular river. It has to be this long so as to get to the other end. It has to withstand a certain amount of weight, right? You want big trucks to go through it. And then you design this tool in order to be useful. It has to work. And this is the way we're going to approach these issues of probabilities throughout. Second problem. And without solving the second problem, the first one is not useless, because probabilities are tools for reasoning when you don't have information. What is the natural thing to do? Well, go seek that information, get it. And you may not get all the information you wanted, you may get a little bit. Well, that could be useful. So then the question becomes, how do we update probabilities when we do get new information? Without solving problem 2, you're stuck in number 1, in which you say, yes, I do know that I'm going to use probabilities to describe states of incomplete information, but how do I even start assigning those probabilities? And in the case that you might be able to assign a probability, how do you learn and improve your awful situation of having incomplete information? We need a tool to do that, and this may come to as a shock to many people, but the tool to do this is entropy. Entropy was originally invented for the purposes of describing thermodynamic systems, the fact that there is irreversibility in the laws of physics when you're looking at sufficiently large objects. And at first, it was something that was associated with, well, a degree of irreversibility that had to do with heat flowing from hot to cold, and you would compute it using various formulas involving heat. And people were very unhappy about what it meant. It wasn't obvious, and well, it's not obvious up to this day. But from heat, it evolved into a quantity that might actually describe degrees of disorder, another sort of vague concept. Then it was associated to amounts of missing information. A probability distribution with high entropy is one which is very broad, and therefore there is an incredible amount of real information that's missing. If you had that information, the probability would be very, very narrow. So the tool for updating is entropy. And finally, there is a third problem that we might want to address to have this full scheme under control, which is if the purpose of all of this is going to be the probabilities describe a certain state of knowledge or incomplete knowledge, is your state going to be given by this probability distribution or that one? Does it make any difference? When you update from one probability distribution because you acquired some information to another probability distribution, did it make any difference? Can we distinguish probability distributions? If your goal is going to be to pick a probability distribution among many, how many do you have? Are there a lot and it's easy to pick one? Or are they too close together and doesn't make any difference? So that kind of problem, which is absolutely crucial, is remarkable, and this again may come as a surprise to many of you, but the tool to address these things is geometry. The subject is called information geometry. Clearly, in principle, there is nothing here to suggest that the geometry of spaces of probability distributions has anything to do with the geometry of the world. You know, geometry in your kitchen, right? You have Pythagoras theorem, and you have all sorts of, parallel lines, and if you have gravity, the lines are no longer parallel, and all of that. Is there any connection? There is a Pythagoras theorem when you do this studying the distinguishability of distributions. There are parallel lines. There are notions of parallelism. There are notions of area, of volume. That's remarkable. It's exactly the same mathematics. So once you look at these three concepts that we see here appear in the context of reasoning with incomplete information, the question that immediately ought to arise in our minds is, reasoning with incomplete information involves probabilities, involves entropy, involves geometry. Those concepts appear in physics everywhere. Could it possibly be that the laws of physics are not directly, immediately laws about nature, but might be laws about nature a little bit indirectly? That the laws of physics that we have are really laws for making inferences about nature, rather than being about nature directly. And the main purpose of this course is precisely to argue that, yes, the reason we have probabilities in statistical mechanics and in quantum mechanics is because we are reasoning with incomplete information. The reason we have entropy all over the place when we're doing physics is because we're trying to incorporate information into those probabilities to have better probabilities. And finally, the reason we introduce geometry immediately into any problem in science, because we know it's going to work, this is a tool that works, is because we want to distinguish neighboring things. We want to see, can we tell them apart? If they're close together, we confuse them. If they're far apart, they're easy to distinguish. Those are inferential concepts. And they do come from, or at least we would like to be able to argue, that they're coming from the fact that science itself is completely inferential. Very good. So this sends us now, after that brief introduction, what I'm going to do is I'm going to stop here for a minute and start a new video in which we're going to talk about the design of probability theory.